like to welcome everybody to this S2S webinar on subseasonal forecasting in a range of different regions and with a range of different methods. And we have an exciting lineup of speakers who will tell us a bit more about their research. So we have Dominik Büeler starting off, and then Paula Gonzalez, Kirsten Mayer, and Matt Newman, who will present their research today. So thanks everybody for joining, and I think we'll just get started right away with Dominik's presentation.
So yeah, thank you, Daniela, and thank you also for giving me the opportunity to present my work here that I have been doing as a postdoc at KIT. And as you see, I'm going to talk about the year-round subseasonal forecast skill for Atlantic European regimes. And I think I will not have to go into detail why it's interesting to look at regimes in subseasonal forecasts, but I just want to briefly introduce which regimes we're looking at and why we do so. So you might be all familiar with these four classic seasonal regimes in the Atlantic European regions, which you see here for the cluster mean, the positive and the negative NAO. Then we have a blocking type regime over Europe and the Atlantic ridge regime. And these regimes are, the predictability of these regimes is relatively well understood for winter. However, we still lack a systematic understanding of how well we can predict them throughout the year. So for this reason, having a bit of delay, here it comes. So for this reason, we look at a relatively new set of 7 regimes. And the key advantages of these regimes are, first of all, that they're defined year-round, as I said. And second, like the higher number of regimes allows a bit to give a more detailed view on surface weather modulation than the classic 4 regimes typically do. So when you see these regimes here defined in error interim, so we have 3 cyclonic type regimes at the top and 4 block type regimes at the bottom. So there's the Atlantic trough here on the top left, and we have the zonal regime that strongly corresponds to the positive NAO, and we have a Scandinavian trough. And then for the block regimes, we have the Atlantic ridge that corresponds to the one in the original definition. But then we have kind of 2 flavors of the classic blocking regime. We see here the European blocking and the more northerly located Scandinavian blocking. And finally, we have the Greenland blocking that is strongly linked to the negative NAO. So I'll go ahead like this. So maybe just briefly, why do we care about these 7 regimes? So I'm just giving you a glimpse on recent or earlier studies that have used these regimes. So for instance, on the left, you see that one study looked at how they are useful to explain wind electricity generation in different European subregions. In the center here, 2 studies looked at how they modulate extreme precipitation or near surface temperature. And on the right, we have been involved in a study in which we used the 7 regimes to try to predict enhanced mortality in the UK, for instance, due to cold waves. So with this, I hope I convince you that it's important to understand how well these can be predicted throughout the year. So, and this brings me to the questions I want to address today. So in the first part, I will really look at the question, how well do the subseasonal forecasts predict these 7 regimes? And in the second part, I will touch upon the question of how seasonal or planetary scale processes affect the regime forecast scale. So the data I'm using is ECMWF S2S reforecasts over a period of about 21 years. And as you all know, they come with 11 ensemble members and 46 days lead time. And maybe a side comment, I'm currently implementing this also in all the other S2S models, but this is still work in progress. So before I show you some results, just briefly, how do we identify these regimes? So we basically start with the cluster mean anomalies in error interim, and then we take the instantaneous geopotential height anomalies in the ensemble and project them onto these 7 cluster means. And then we normalize them seasonally in a way that we end up with this so-called weather regime index, which you see here for one example forecast. So you see how the ensemble with lead time here on the x-axis projects into these 7 cluster mean. But we ultimately want to reduce this to a kind of a 1-dimensional view or a 2-dimensional view. So we want to know which regime is active at each lead time step. For this, we apply a set of lifecycle criterion. So we check at each lead time step which regime index is maximum above a certain threshold and persists for longer than 5 days. And then we end up with this final forecast product, which you might also know from the ECMWF webpage. So this shows basically the life cycle predictions with lead time on the x-axis. And this also introduces this no regime category in gray for those memories in which none of the 7 regime fulfills the life cycle criterion. And this is the basis now that we verify against the error interim observation, so to say, at the bottom here, this vector at the bottom. So, and this will bring me to the first result. So in the first part, we looked at, or before looking at skill, we really checked how certain properties of these life cycles are predicted or captured on average in the model. And 2 such properties are the life cycle duration and the number. So duration means really between the onset and the decay. So we really look at events, life cycle events. And I'm going to show you plots like this here, in which you see these box and whiskers. They basically show the life cycle length, shown here on the left y-axis. And the filled one are always the forecast, and the blank one are error interim. Oops. And then the 2 diamond symbols, they show the total life cycle number, which is shown on the right y-axis. So let's look at this for winter first. If we first focus on verifying the forecast a bit, we see on average, so this is the dots here, and the life cycle length can be predicted relatively well. So, and then when we look at the life cycle number, the diamond symbols, and compare them between the forecast and the error interim, we also see that overall there's no large mismatches in this respect. So the model or the forecast captures these climatological properties relatively well. When we go to summer now, we see that also on average life cycle length is relatively well predicted, except the overestimation here of the zonal regime, the zonal duration. And I forgot to mention actually that there's an underestimation of the Scandinavian blocking regime here in winter, which is maybe the most striking mismatch, let's say. And coming back to summer, as I said, also the duration is relatively well captured. But when we look now into the life cycle number, so the diamond symbols, we see that the mismatches become larger. So for instance, as you see here, the Scandinavian blocking regime is under-predicted in a sense that the forecasts have too few Scandinavian blocking life cycles in summer, but rather too many European blocking life cycles. And this is reflects a bit a general thing we find that I cannot show here due to time reasons, but we found that overall, even in the calibrated forecast, the large-scale biases in summer are much bigger than in winter, and this also reflects in biases in regime occurrence, of course. And apart from this verification aspect, there's also physical aspects. So for instance, the 2 most persistent regimes are the ones, the zonal regime and the Greenland blocking in winter, and the least persistent is the European blocking. But this changes in summer, where the European blocking becomes most persistent, whereas, for instance, the zonal becomes least persistent, but also very rare in terms of occurrence frequency. And this is something we have to keep in mind to understand, and there's some differences in skill later on. And we did the same analysis here and verified the transitions between these regimes, but unfortunately, I do not have the time to show this here. And I would like to continue now with looking at actual forecast skill. So what I'm showing here as a first, just introductory slide, so to say, is the Fairbrother skill score for the year-round, for all year and for all regimes together. And what you see here on the right is just to illustrate what we do. So we verify the model forecast against the error interim occurrence frequency at a specific calendar day. This is our reference forecast here. So, and another side comment, I will mainly focus on the level of 0.1 because we argue that this is still a kind of a useful level of skill to look at. So when we focus on this level, the skill horizon on average is about 2 weeks, and this is consistent with what previous studies have shown. But of course, now it's important to look at individual seasons and individual regimes. And this is what I'm showing you here, now you see the seasonal skill for all regimes on average. And now we see strong and significant differences. So the skill horizon in winter, in blue here, is about 5 days longer than in summer and spring, and about 3 days longer than in fall here, this line. And of course, to some degree, these are intrinsic or due to intrinsic predictability differences. So we know that winter is generally better predictable than summer, but nevertheless, when you remember, I said that the biases in summer are still quite large in the model. So if we manage to improve, then we might also manage to further improve this summer skill here. The next important step is to look at now again the year-round skill, but for individual regimes. This is what you see here. And the most striking result I will mention first. This is basically this light green line, which is the European blocking skill. You see this drops fastest and also reaches the shortest skill horizon compared to all the others. And it's also interesting that the skill horizon is much shorter than for the Scandinavian blocking, which is strongly related. And this is interesting in the sense that we know about these problems in blocking. This is nothing new, but with our new definition of regimes, we show that it seems to be more this centrally located European blocking that causes the major problems throughout the year. So, and now I went one too fast. So, and the other, like, let's say the winning regimes are this zonal regime, the Greenland blocking, the blue and the red line, which tend to have the longest skill also throughout the year. Of course, now the question arises, how do the individual seasons contribute to this skill throughout the year? So I'm showing you the same plots here again for the individual seasons. And now you see the skill scores become less robust due to the smaller sample size, but we still see important and interesting differences. So first of all, let's focus again on the European blocking. So it might be hard for you to see, but we basically all 4 seasons show that the European blocking is the one belonging to the regimes with the lowest skill, basically. So this really seems to be a year-round problem. However, the relatively higher skill of the Scandinavian blocking of the dark green line is only there in summer, in which here you see the Scandinavian blocking tends to have the longest skill, and also to some degree in fall. It's hard for you to see. But in winter and spring, you see both green lines basically are the ones with the lowest skill. So it's really both blocking type regimes in summer and winter, or in winter and spring, having these problems. On the other hand, we see that the strong skill of the Greenland blocking and the zonal regime in blue and red, is clearly dominated by winter here, in which you see these 2 regimes have remarkable skill well beyond 20 to 25 days, and up to 10 days longer than 2 blocking regimes. And this clearly shows that we do have windows of predictability already in state-of-the-art models. And similarly, in spring, we see this Atlantic trough regime has also a remarkable skill horizon, which is even up to 10 to 15 days longer than, for instance, this European blocking regime. And of course, the question is now, if we want to improve models, where do these differences come from? Of course, that's a very complex question, but maybe one thing that we should focus on is its differences in intrinsic predictability. And these are for sure to some degree related to the differences in persistence. So for instance, the Greenland and the zonal regime, these 2 NAO type regimes, are certainly driven, or the good skill is driven by their long persistence. Whereas the European blocking, which is the least persistent one, might also contribute to its bad skill. And likewise, in summer, when the zonal regime tends to have the lowest skill, it might be partly driven by its relatively short persistence. Nevertheless, although the European blocking tends to have the highest persistence in summer, it still has a relatively bad skill. So this shows that this is one aspect, but of course, there's internal errors in the model that need to be improved. So with this, I've shown you how well these regimes are predicted in general, independent of any external factors. But as a second step, I would like to show you how, let's say, the most important drivers for the Atlantic European region affect the skill of these regimes. And one of these drivers is the stratospheric polar vortex in winter. So what we did is we looked at the state of the polar vortex at forecast initial time. And we checked, so how is the skill for all regimes together in red in the forecast starting with the 10% strongest polar vortex states, and in blue the ones with the 10% weakest polar vortex states. And this is compared to the black curve, which is basically the normal states. So, and we see the uncertainty is relatively big, of course, but nevertheless, we see a tendency in the medium range towards enhanced skill after both extreme states. But the interesting thing is that when we go to the subseasonal lead times, we see that it's only the strongest polar vortex states that tend to increase the skill horizon, whereas the weak polar vortex states tend to even reduce the skill to some degree compared to the normal states. Just to see how robust this is, we did the same analysis for the 20% strongest and weakest states. And qualitatively, this asymmetry between strong and weak states still stays the same. However, also the strong states do not outperform basically the normal states so clearly anymore in subseasonal lead times. So it seems that the polar vortex really needs to be truly strong for giving this enhanced predictability. And this is interesting, this finding, because we also found something similar for European 2-meter temperatures, in which we found that they are more predictable after strong than after weak polar vortex states. And I think it's important to see that many previous studies often focused on these weak polar vortex states or sudden stratospheric warming. But I think it shows here that the model still struggles to exploit this predictability, and it's something that needs to be improved. And as a last step, I'd like to show you how the MJO affects the skill for these 7 regimes. So what we did first, we looked at the seasonal skill for all regimes after an active MJO in blue compared to a non-active MJO in black for the 4 seasons. And as you see, there's no big modulations in skill, which was a bit surprising to us at first glance. But to understand this better, we had to look into the individual phases. And this showed us that this comes because different phases actually tend to increase the skill, whereas others tend to decrease the skill. And in total, this gives kind of a negligible effect on just looking at the active MJO. And I'd like to give you, with this final slide, an insight into, again, the year-round skill only, how the 8 phases affect the skill for the 7 regimes. And the most striking modulation is this increase in the skill horizon of several days after phase 7, as you see here, and also more in the medium range after phase 4. And probably the biggest reduction in total is the reduction after phase 2. And we also did that for the individual seasons, and I want to show you this quickly. So the increase in phase 7 is most strongly driven by winter and spring, as you see here at the top. But then when we look at phase 4, the year-round skill modulation, we see it's mostly driven by fall, actually, but to some degree also by winter. On the other hand, the reduction after phase 4 is mainly driven by spring and by fall. And so this really shows that a quite complex pattern of how these different phases affect the skill over Europe during the different seasons. And it's clear that we also have to look at various seasons and not just winter to understand the influence of the MJO. With this, I'd like to come to my conclusions. So at the first step, I showed you that overall the subseasonal forecast performance is best in winter and worst in summer. And this is actually both the case in terms of biases, which are largest in summer, but also the smallest skill in summer. So for the individual regimes, we found the lowest skill, for the European blocking, significantly lower than all the other regimes, and this including the Scandinavian blocking, which is related to the Europe blocking. On the other hand, we found that the year-round skill horizon for the zonal and Greenland blocking regimes is longest, and this is likely influenced by their coupling to the stratosphere in winter, giving very persistent regimes. So we do have existing windows of subseasonal predictability already in state-of-the-art models. And in the second part, I showed you that the winter regime skill horizon is longer after strong polar vortex states, but shorter after weak polar vortices. And it seems that this is only true for really strong polar vortex states. And finally, we found that the year-round regime skill tends to be enhanced after phases 7 and 4 of the MGO, but reduced after phase 2. But it's important to mention that this is the year-round picture, and we have to really look into the individual seasons, because we see that not just winter, but also spring and autumn strongly influence this. And I'd like to wrap up with this kind of box here. So our study shows actually promising potential for further improving year-round subseasonal forecasts for regimes. And this can be achieved, first of all, by removing the large biases in summer, by better understanding and model the blocking in Europe, particularly these different subtypes that might have different dynamical drivers, and finally to improve model responses following particularly weak polar vortex states and specific MGO phases in winter and the transition seasons. And with this, I'd like to thank you and just give this mention that this work is currently under review, and we hope that it will be accepted at some point, that you can have a more detailed look at it. Thank you.
Thank you very much, Dominik, for this nice presentation. So we have time for a quick question, if there are any, for Dominik. If you have a question, feel free to just speak up.
I think there was one in the chat, but I'm not sure if I see the chat.
Yes, so there is one from Ignacio. Ignacio, would you like to read it yourself, or I can do it also?
Yes, I can ask directly. So if you can say again the difference between the life cycle length and the life cycle number, because I missed it. And if you can say how the no regime category is assigned when you say which regime we are in. Thank you.
So you mean, oops, I'll briefly go back here. So you're referring to the verification of the length and number, right? That was your first
Yes,
question.
because I did not understand what the number means, actually.
Oops. Oh, yeah, okay. Yeah, maybe, whoop. My computer is a bit overwhelmed. I'm sorry. So, yeah, maybe just briefly. So the life cycle, when I talk about the life cycle, so there's one way of checking at each lead time step which regime is active with these life cycle criterion. And as a last step, what we do is we merge all consecutive days in one life cycle to one life cycle object. So, and then we can objectively identify an onset and a decay, and the time in between is then our life cycle, which is at minimum 5 days, but it can go up to 40 days. And all these events we define as life cycles, and this we count these numbers of life cycles in the model and compare it to error entry. I'm not sure if this answers your question.
Yes, I mean, I understand that there is persistence in the how many days the regime stays, but the life cycle number, I don't think I got it. The diamonds, I think, are right.
Yeah, so in DJ, so in this plot, for instance, exactly the diamonds. So what I do, I take these 900 forecasts here and just count how many of these phases of a consecutive zonal regime, for instance, at each day I have, or numbers of life cycles, basically. So yeah, I don't know how I should, or maybe I can show it here. It's easier. So for instance, this yellow bar here in Erythrium, this would be one life cycle count for this yellow Atlantic ridge. And this is what we count in all the 900 forecasts. Yeah.
Okay, so thank you very much. We have to move on to the next talk, but Dominik, there was a few questions in the chat, so you might want to look at those as well.
Okay, yeah, thanks.
So our next speaker is Paula Gonzalez, and feel free to start sharing your screen.
Yes, thank you. So yeah, first of all, thanks for the invitation to be part of this. I'm going to be presenting some work from, oops. from a rather large group of people from NCAS and the University of Reading. This is our research on the use of weather regimes for prediction of high impact weather over Southeast Asia. This was part of a project that had three objectives. The first one was to identify a set or different sets of weather regimes for Southeast Asia that were able to describe both the large-scale circulation and the synoptic scale variability. We did that through a one-tiered and a two-tiered approach. And then the second objective was to relate those weather regime sets to known modes of variability over the region and their impacts, of course. And the results from those first two objectives are part of a manuscript that has been submitted to QSHA. Finally, the last bit, that's the one that I was mostly involved with, is to demonstrate the use of these regimes for improving long-range forecast over the region. So that's what I'm going to focus most of this talk on. Despite that, I'm just going to briefly describe the methods that we used and some of the initial results. So as I mentioned before, the idea was to capture both the large scale and the synoptic scale variability over the region. So the approach that was tested on the project was to start with a two-tier approach in which an initial set of patterns was obtained for this larger blue domain. And then for each day on each of these clusters, they were subset into the smaller domain. And over that, over the whole method, we obtained 8 clusters for the tier 1, and then between 5 and 8 subclusters for the small domain. So through the two-tier approach, we end up with 51 patterns, and those 51 patterns were there compared with a flat set in which all days were clustered over the small domain without distinction for 51 patterns so that they are comparable. This was done using ERA 5 850 wind vectors, and no kind of seasonal subsetting was considered beforehand. And just to describe the overall frequency of the patterns, this is done with the wheel plot on the bottom right, and we see in the inner circle the tier 1 domain, so the large scale patterns, and then each one subsetted into the tier 2 domains in the outer circle. So just to give you an idea of the flavors of these patterns, we have here the tier 1 clusters, but only shown over the small domain. So for those of you who are familiar with the climate of that region, you can see that this is basically just describing the overall seasonal cycle of the monsoon activity over the region. So we have some patterns in which we're clearly seeing monsoon phases, such as in regime 4 and regime 5, and then we have some transition phases, such as the northward transition in regime 3 and southward transition in regime 7, and so on. But at the same time, we were able to see that these regimes are connected with known modes of variability, such as El Niño and MJO. And as we can see, hopefully, on the next slide, yeah. It's quite easy to see, for instance, the connection with El Niño if we just take this is basically showing the seasonal frequency of the tier 1 regimes in these colors as a function of the day of the year on the x-axis, and on the y-axis we see the years that have been subset into La Niña and El Niño years, and we can see, for instance, that if we focus on the frequencies of the blue and the orange regimes, we can clearly see that the orange one is more frequent during La Niña years, and the blue one is more frequent during El Niño years. And the same type of connections are also found with the Madden-Schroeder oscillation, but also with other known modes of variability over the region, such as cold surges, tropical cyclone activity, the Borneo vortex, equatorial waves, and so on. So a very detailed analysis was performed. This was mainly led by Emma Howard, and we saw that there's a very strong connection, and also with a very strong connection with the seasonality of the occurrence of these phenomena, which is what we were hoping to capture through the use of these very large sets of clusters. But more importantly, we are interested in capturing their connection with precipitation, and in particular with extreme precipitation. So if we just focus on the overall variance of precipitation over the region, we were able to see that the tier 2 and the flat approaches, they capture similar amounts of the explained variance. In this case, it's the explained variance of the anomalies. So with respect to the seasonal cycle, so this is not a very large number. It's around 12% at the most. And the only places where we see that the flat approach somewhat outperforms the tier 2 is around the region where we have most of the influence from tropical cyclones, or around the Philippines mainly. But then if we actually want to focus on the extreme precipitation, what we did here on the bottom plot is to account for the Breyer skill score of precipitation exceeding the 90th percentile, but under a perfect forecast hypothesis, right, where we assume that we have perfect knowledge of the regime in which we're at, and also of the seasonally varying phase of the Madden-Julian oscillation, because it's a known driver for variability over the region. And what we can see is that both the flat and the tier 2 sets, that are the darker green colors, tend to outperform the only knowing the phase of the Madden-Julian oscillation, and obviously they all have positive potential skill for capturing the exceedance of the 90th percentile. They seem to also have a seasonal cycle, as you can see from this plot as well. So then we can now focus on actually moving to the prediction. So for doing that, we consider the regime representation by the glossy 5 system. So we use the hindcast from the S2S dataset, corresponding to a full year of starts in the period July 2017 June to 2018, and the 23-year hindcast period. From this system, we have 4 starts per month and 7 ensemble members. So what we did was for each start day, lead time, and ensemble member to assign a regime from each set by projecting them to the ERA 5 centroids. There's a very slight difference in how they were designed and how they are assigned, because in the case of the model, we only have midnight winds from the S2S dataset. But that tends to just explain slight differences between what would be the analysis and the first forecast time. And here we started by studying the representation of the regimes, and in particular to just look at the frequencies and durations of the regimes in the model and compare them with ERA 5. So, for instance, if we focus on these line color plots, we have here on top the tier regimes and the flats on the bottom. We can just focus on the tier ones. And in the first column, we have their overall frequencies if we consider the ERA set. And then this is what we obtain from the hindcasts and as a function of lead time. And we can see that it all starts quite well to begin with, but some quite obvious biases start to appear. The most noticeable one is a drift towards a higher frequency of these purplish colors that are the regime 5 at the expense of the reddish colors that are regime 4. In this case, it means that there is like a bias towards an eastward extension of the boreal summer monsoon in this system in particular. And regarding the durations, we have these little tables here on the bottom, and we found that there is in general an overestimation of the tier 1, the tier in general, the tier regimes. There's a slight overestimation of the duration of the regimes. Then we moved to actually looking at the skill of the system to assign the regimes. And what we found, we looked at this through the use of the rank probability skill score. And we have here a comparison between the flat and the tier in blue and red. And also a comparison between between the two of them. So what we see is that both methods, they are able to capture the observed regime until around day 11 or 12, and they seem very similar with regards to their skill score. The comparison actually shows that the tier regime is always outperforming the flat ones. And if we look at the plot on the right, this is actually showing us that when we consider just the rank probability score, which is a measure of the error, we see that the tier regimes has overall smaller errors in the assignment. And it's important to note that we are considering here a regime condition seasonally varying climatology, because we know that the regimes themselves contain a lot of information about the seasonal cycle. So it's a fairer comparison if we use that as a reference. So knowing that we have some skill in the assignment of the regimes, then the next step is obviously to look into considering regime condition forecast for extreme precipitation. So over here, we're just considering the example of the exceedance of the P90. And from the Glossy 5 system, we can take two sets of information. We can basically just start with their forecasted probability that comes straight from simulated precipitation. But then we can also consider the forecasted winds to actually obtain a probability of being in a given regime. So if this probability, we actually combine it with a condition probability of occurrence of precipitation that's been driven by ERA5, and in our case we use NASA GPM precipitation, we can actually obtain a regime condition probability of occurrence, which is what we are going to compare here on the right. So first, we can look at a standard measure for skill, which is the Breyer skill score, in this case, again, for P90. And we are comparing here lead 0 on the left and lead 7 on the right. On the first row of these plots, we are comparing the different methods. So we have the simulated precipitation to begin with, our flat regime condition method, and the tier 1. And for lead 0, we can see that in blue, we have positive Breyer skill scores, which means that we have some skill. And the simulated precipitation only has skill mainly over some ocean regions, right? But over land, even for lead 0, it's very poor. Whereas our methods, they tend to produce moderate but positive levels of skill over most regions over land. We can see that by lead 7 on the right, even those very limited regions of positive skill in the simulated precipitation are lost, whereas the regime condition methods, they tend to keep skill over most regions over land as well. The comparison on the bottom, this is just building on those Breyer skill score between the methods themselves. So this is showing us that the flat and the tier methods outperform the simulated precipitation overall over land, and they tend to do that for both lead times. So we can then move to considering this as a global metric for all land points. So if we look at this initially, this plot on the top left, we have the comparison of the mean Breyer skill score for the two methods. And overall, considering all the land points, this is telling us that they have positive levels of skill extending until around day 12 or 13 in the case of the flat regime, and even further around like 22 days on the case of the tier regime. So we see that the fact that we were able to capture more of the large scale variability is in this case translating into longer lead times, longer skillful lead times in the case of the tier regime. But then the project it's still ongoing, and it is now considering on the work of Sam Ferret. She's been focusing on the effects of temporal and spatial aggregation of these predictions. So we consider two cases, and in the right here is asking ourselves the question of what is the probability of having at least one day of exceedance in the week, which can be very interesting in terms of impacts, right? So knowing that at least we have the probability of having one event, regardless of knowing where it is. And we can see that overall it's not really extending the range of skillful prediction. So it's only providing skillful Brier skills scores for week 1 for both methods. And then we also consider the spatial aggregation of the exceedance into K by K grid points neighborhoods. And what we see in this case is that we do see an increase in the levels of skill as a result of this aggregation. But again, it's not really leading to a significant extension in the levels of prediction. So we have the flag here, which is showing about 2 days of increase prediction skill when aggregating, but up to very, very large regions, right? So this is like 5 by 5 grid points. It's getting closer to 10 degrees by 10 degrees. And in the case of the tier regimes, there's really no extension. And in the case of simulated precipitation, the impact on the initial lead days, it's very strong, but it's mainly because it had no skill to begin with. So it's just providing some more skill in the detection of the events. Finally, we just brought here an example of a case study in which we just picked up an event that had been very significant outside of the hindcast set. And we were able to show that the regime condition forecast here on the big plots were providing us probabilities of obtaining an exceedance event even 2 and 3 weeks in advance. This means that these probabilities are higher than the seasonally varying climatological odds of occurrence. And this had been a very significant event with severe impacts. And in the case of the simulated precipitation, the forecast were really showing weak exceedance probabilities in week 0, but really nothing overland beyond that. So this was encouraging in exhibiting that these methods can be useful over this region. So as a short summary, in this project, we consider 2 sets of weather patterns that were aiming to capture both the large scale and the synoptic scale variability over Southeast Asia. Both sets showed potential predictability for their connection with high impact weather, in particular extreme precipitation. And the Glossy 5 system was generally able to describe these regimes quite well, but with some biases. And our assessment of the skill is showing us that these regimes, and in particular the tier set, is able to provide skillful simulations beyond lead day 20. And these initial results from the temporal and spatial aggregations show that they can yield higher skills, but not really an extension on the useful horizon of these predictions. And that's it for me. Thank you.
Thank you very much, Paula. So we have time for a quick question. If there's anything from the audience, feel free to unmute yourself and say your question yourself. Maybe in the meantime, I have a quick one. You said when you defined the regimes from the model, then you looked at the regimes in error 5 to compare this. What if you would define the regimes only from the model itself? Would you end up with something very similar?
So it's a completely different approach, right? To allow the model to develop its own regimes. In some senses, it can be better at capturing the variability, but it would be questionable how much we can trust the connection between precipitation and the regimes that we are using from let's call it observations, which is really precipitation and era 5, to impose that to build the regime condition predictions. In that sense, it's better to say, okay, these are the regimes that we have identified based on era 5. So we know that in the real world they are connected with this sort of impacts in precipitation.
Mm-hmm.
But it's a valid approach, of course. Yeah.
Yeah, I guess it's a different one.
Mm-hmm.
Okay, thanks a lot. Are there any other questions from the audience? I don't see any at the moment, so but feel free to also post in the chat after Paula's talk. So with this, we would move on. Thank you very much, Paula.
Thank you.
And we move on to Kirsten Mayer, who will present on explainable neural network.
Thank you for the invitation to speak. I'm going to be talking about subseasonal forecasts of opportunity identified by an explainable neural network. My name is Kirsten Mayer. I'm a PhD candidate at Colorado State University, and this is work that I've been doing with my advisor, Elizabeth Barnes. So I know in my title I use the word neural network, and that's kind of like a hot, flashy term. So I'm really hoping in this talk I can do two things: basically kind of demystify what a neural network is, and then two, show you that neural networks can be applied to prediction problems through this subseasonal forecast of opportunity approach. Okay, so I'm going to briefly talk about forecasts of opportunity. Forecasts of opportunity is this idea in general that certain conditions can lead to more predictable behaviors than others. And beyond weather timescales, we must look for specific states of the Earth system or these opportunities that lead to enhanced predictable behavior. So on subseasonal timescales, one example of a forecast of opportunity is the activity of the Madden-Julian oscillation, or the MJO. The MJO is shown here as this propagating signal of outgoing long-wave radiation in the tropics here. And when the MJO is active, we can use information about what's happening in the tropics to predict what will happen in the Northern Hemisphere in the coming weeks. So how can we utilize neural networks to identify forecasts of opportunity for subseasonal prediction? So before I get into this topic, I'm going to briefly go over what neural networks are, specifically what artificial neural networks are, or ANNs. So basically, we normally think of neural networks as data goes into this black box, something happens, and it pops out some sort of prediction that we're looking for. So what is actually happening inside this black box? So an artificial neural network takes inputs, which are, for example, in this example, x1 and x2, multiplies them by weights, w1 and w2, and sums them in what's referred to as a node. And so far, you can see on the right side of this equation, that this is just multilinear regression. But what makes an artificial neural network more than multilinear regression is this activation function. So you can think generally as an ANN is this linear regression with a nonlinear mapping by what we refer to as an activation function. So then when we say that we're training a neural network, we're just determining these weights and biases that minimize this loss function that we prescribe, which is similar to linear regression. So we can have more than two inputs, for example, thousands of inputs, such as like a map. So we can have more than two. We can also have more than one node, so these gray circles here. And then we can also have more than one hidden layer. So for example, this has two hidden layers, each of multiple nodes. Then there's something called an output layer, which we often refer to as our predictions. So you can imagine that ANNs can get very complex very fast in terms of how many nodes you have in a specific layer and how many layers you have. But this complexity and nonlinearities of the ANN allow it to learn many different pathways for predictable behavior. So once your neural network is trained, you have an array of weights, these lines here, and biases, which can be used for prediction on new data. So now I'm going to apply a neural network to identify forecasts of opportunity and to see if it can do so. So there's two questions that I'm asking. First, when do we see these periods of enhanced predictability? Or can we identify these forecasts of opportunity? And the second, as a scientist, we want to know what the neural network looked at to know that there was predictability in the first place, or how it identified these forecasts of opportunities. So to approach this question, we set up a neural network that took in outgoing long-wave radiation into its input layer here. We pass it to two hidden layers, and we tasked it to predict the sign of the 500 hectopascal geopotential height 3 weeks later, not 300, 3 weeks later. So this is a binary classification problem, meaning that we're just predicting the sign instead of a number per se. So either a positive or a negative sign. So how do we identify opportunities for enhanced predictability using this neural network setup? So to do this, we use something called the Softmax Activation function, which is applied at the output layer. So in a typical neural network, you can get output that looks like this. For example, this neural network is predicting that the sign of the circulation over the North Atlantic is positive because this number here is larger than this number here. When we apply a softmax activation function, it converts these numbers into values that sum to 1. So you can think of these as a probability, or what we refer to as model confidence. So the higher this number, the more confident the model was in its prediction. So in this case, the model was very confident in its prediction that the sign of the circulation was positive over the North Atlantic. So these high confident predictions may indicate forecasts of opportunity. So let's see if this is actually the case. To do so, we made a plot of accuracy on the y-axis versus neural network confidence on the x-axis. Where on the left-hand side, we have low confidence in the prediction, and then on the right, we have high confidence in the prediction. And so you can see when we have relatively low to medium confidence in our prediction, we have accuracies that hover around 55 to 60%. But as we increase this confidence threshold, we can also see that our accuracy greatly increases as our confidence increases. So as our confidence threshold increases, our accuracy increases. And we would expect this because we know a phenomenon like the NJO and the specific region of OLR that we are using that lead to enhanced predictable behavior. But this is truly an opportunity because as we increase our confidence, we also lose the number of samples we can use, samples that are confident to make these predictions. So with this confidence, we can determine when we have periods of enhanced predictability. So now we answered that we can use model confidence to identify these forecasts of opportunity or these periods of enhanced predictability. But then the second question is, why is there predictability in the first place, and where is the neural network looking to determine that predictability? So in order to do so, we use something called Layerwise Relevance Propagation, or LRP. This is a neural network explainability technique, which basically asks, what did the model learn? So in our case, we're asking, what are the relevant physical structures of the outgoing long-wave radiation in the tropics for prediction over the North Atlantic 3 weeks later? Okay, there it goes. So here's an example of a layer-wise relevance propagation. So let's say we have a trained neural network that's been tasked to predict whether there's a cat in a given image. And let's say this trained neural network gets this image and correctly predicts that there's a cat in the image. Then we want to know what the neural network looked at to determine that there was a cat in this image. We can obviously see that there's a cat in this image, but what does the neural network pick out as important for this prediction? So what layer-wise relevance propagation does, excuse me, is backpropagates this term called relevance, which is defined here. It backpropagates this through the trained neural network to give you a heat map of the relevant pixels in the input that led to your correct prediction. So as you can see here, the neural network was highlighting this outline of the cat, specifically its ears and its nose, eyes, etc., to determine that this was a cat in the original image. So in our case, we input outgoing long-wave radiation, not a cat, to determine the sign of the circulation 3 weeks later over the North Atlantic. So let's say that our neural network predicts that there's a positive circulation anomaly over the North Atlantic. We want to know, then, using Layerwise relevance propagation, what the relevant physical features of outgoing long-wave radiation were to make this correct and confident prediction of the sign of the circulation 3 weeks later. So we will be getting, instead of a heat map of a cat, a heat map of the regions of this box here where the outgoing long-wave radiation was important for this prediction over the North Atlantic. So what are these relevant physical structures of outgoing long-wave radiation in the tropics for prediction over the North Atlantic 3 weeks later? So here I have a composite of all the confident and correct positive sign predictions for the circulation over the North Atlantic. In the shading, I have this heat map that was similar to the cat example. And then in the contours, I have the average outgoing long-wave radiation anomalies that the neural network is highlighting. So you can see that the neural network is highlighting the Indian Ocean and into the maritime continent, as well as the Western Pacific. And this looks a lot like MJO phases 3 and 4. This is consistent with previous research, as we know that MJO phases 3 and 4 leads to an increased occurrence of the positive NAO, which you can see here in our region is a positive sign anomaly. So this is consistent with research that we know. So for these confident and correct negative sign predictions, we can see again that the neural network is highlighting this maritime continent region, as well as the Western Pacific, which looks a lot like MJO phases 7 and 8. And again, we know from previous research that the MJO and the NAO are linked, and MJO phases 6, 7, and 8 have been shown to lead to an increased occurrence of NAO, the negative NAO phase, which is also consistent. So LRP has identified these MJO-like dipole structures, which we know from previous research lead to the corresponding sign in the North Atlantic. But you might have noticed that just west of Hawaii, we have this hotspot that I haven't mentioned yet. And so I'm going to get into this now. So with layer-wise relevance propagation, we get a heat map for each prediction that is made. So therefore, we can understand that for each correct and confident prediction the neural network makes, what the neural network was looking at in the original input image to determine that this was the correct sign. So if we cluster our LRP maps, we can get certain structures of our outgoing long-wave radiation that could be used for forecasts of opportunity. So on the left here, we have cluster 1 for the positive sign predictions, again highlighting this Indian Ocean maritime continent region and the Western Pacific. And then for cluster 2, we see that it is mainly highlighting that the convective region over the maritime continent for this prediction. For the negative sign predictions, which is the ones that had this hotspot over Hawaii, or just west of Hawaii, we can see that the neural network in cluster 1 is highlighting this MJO-like dipole structure for MJO phases 7 and 8. But then cluster 2 is only highlighting this hotspot just west of Hawaii with no MJO-like structure in the maritime continent and Western Pacific region, which suggests that this could be a new forecast of opportunity for prediction into the North Atlantic. You might have also noticed that there's a hotspot over Saudi Arabia in both of the cluster 1 and cluster of negative and positive predictions. We're hypothesizing that this could be related to the MJO, to the NAO, and back to the MJO connection, where following the NAO, there tends to be a significant modulation of the tropical upper troposphere zonal wind over the Atlantic Africa region, which has been hypothesized to play a role in MJO initialization. And so the neural network may be identifying that this region is important to initialize the MJO, which leads to the correct sign of the NAO over the North Atlantic. So clustering can be a useful tool for identifying one or more forecasts of opportunity identified by our neural network. So we can use model confidence to identify these forecasts of opportunity, and then using these forecasts of opportunity, we can understand what the neural network looked at through Layerwise relevance propagation to identify where these periods of enhanced predictability come from. So I'd also like to give a general workflow for this process so you can apply it to your own work. This doesn't just have to be applied to subseasonal prediction, though this may be exactly what you're interested in. You can identify a research problem to address specifically related to prediction. You can create this neural network to answer this research question. Then you can use model confidence to identify opportunities for enhanced predictability, and then use LRP or neural network explainability techniques to determine the trustworthiness of your forecast of opportunity that was identified by the neural network. But you can also use it to identify new patterns of predictability. So in conclusion, we can use these neural networks to further understand subseasonal prediction, one, through this model confidence to identify opportunities for increased accuracy, and two, through layer-wise relevance propagation to really open up that black box that is referred to as a neural network, to learn how the network made its prediction and possibly identify new sources of predictability from extracting knowledge from the neural network. This work has been recently published in GRL with the DOI here if you're interested, and I'd be happy to take any questions.
Thank you very much, Kirsten. Very nice talk. So do we have any questions from the audience? Feel free to unmute yourself if you have one. Maybe I can have a quick one at the beginning. To what extent can you determine lags from this methodology?
You mean how did we determine the lags?
Like how do you know how far in advance? Like because you said, for example, that you have this pathway, you know, from the MJO, NAO, MJO. Like how can you tell what comes first and how things cause each other?
Oh, I see. Yeah. I wouldn't say that this method directly identifies which direction the pathway is, but it can identify for you a starting point and where to look for a specific pathway.
Mm-hmm. Okay, thanks a lot. So basically afterwards you would go in and try to find out how these are connected in the first place.
Yeah, exactly. You use what you know as a domain scientist to truly understand what the neural network is doing.
Mm-hmm. Any more questions for Kirsten?
Yeah, I had one in the chat, actually. I guess I can just ask, which is sort of related.
Yes, please go ahead.
Which is just, so I might have missed this, but how do you know that these OLR hotspots are the MJO as opposed to, say, ENSO? More specifically, how are you determining what the timescales are associated to these hotspots and these LRP maps?
Yeah, so what we're predicting is filtered for subseasonal timescales. So the input that the neural network is highlighting is specifically for a subseasonal signal within the North Atlantic.
ENSO has plenty of subseasonal power.
Yes, and we're not trying to just truly identify the subseasonal frequencies within the outgoing long-wave radiation. We want to see what the neural network was looking at to get an accurate prediction over the North Atlantic. So we're not filtering specifically for example, the MJO, but the neural network has identified some MJO-like structure, which we know as domain scientists that is important for the prediction over the North Atlantic.
Okay, I see there's one more question from Ricardo in the chat. Would you like to speak up yourself, Ricardo?
Yes. Hello. Yeah. Can you hear me? Yes, probably.
Yes.
Okay. Very nice talk. Thank you very much. I was wondering if you use convolutional neural networks, now you can identify patterns that afterwards you could relate to those events. What is the advantage of your method with respect to using a convolutional neural network?
Yeah, so a convolutional neural network could also be applied to this problem. Layerwise relevance propagation hadn't been shown at that point to be very good at determining what the actually identifying these regions. So CNNs could be used, but they're less explainable in general than a very simple artificial neural network that we can use. And an artificial neural network seems to be sufficient for addressing these types of questions, but you can use a more complex model to possibly get higher accuracies in this type of problem.
Thank you very much.
Yeah, thank you.
Great, thanks everybody. And thank you, Kirsten, for the nice talk. So we move on and feel free to ask further questions in the chat. So we move on to Matt Newman, who will tell us more about the NAO.
Okay, that, make sure I got that right. That's correct, right? Yeah.
That's great.
Okay, thanks, Daniela. Thanks for inviting me to give this presentation. I'm going to be talking about work that I'm doing with John Albers, also here at series. In fact, John is the lead on both of the papers. Our interest is related to what Kirsten was talking about in her previous talk, which is how do we identify high skill NAO forecasts ahead of time? We know that S2S skill on average is low. It's just kind of an unfortunate fact of life, but the weather noise is going to still be so large on these timescales that inherently average skill is low. So we're looking for those times when we can identify ahead of time that the skill is high. And that's important because when we issue these forecasts, we need to be able to be confident about them, particularly when we go to users and say, here's our forecast. And so important also for confidence is being to identify dynamically why these high skill forecasts have the high skill that they do. So both of these are important to us. And the way we address this is with an empirical model of dynamics called a linear inverse model. And the idea behind a linear inverse model is very simple. Basically, if you have a highly nonlinear system, but the nonlinearities tend to evolve much faster than linear dynamics does, then essentially what you have is a system where there's a lot of integration taking place. Slow dynamics are integrating the faster dynamics. This tends to make variability more Gaussian, and in a limit where there's essentially a very large difference in these timescales, you'll end up with an effectively linear system, where in this case, you can describe it in terms of linear dynamics and a residual forcing, which can be quite large, which is just noise. In other words, it's entirely unpredictable on the time scale of the linear dynamics. So this very simple relationship can, in fact, also be determined empirically, and that's what we do. Again, keep in mind, this is an effectively linear model. It's not the same thing as a linearization. It implicitly includes a parameterization, a linear parameterization of nonlinear terms. Also important is that the dynamics are asymmetric. In other words, it matters where you are and variables interact differently. Shear obviously ultimately gives you asymmetry and advection as the most obvious example. And so that leads to something called non-normal linear dynamics, which mathematically means that the eigenanalysis of this matrix linear operator gives rise to a set of eigenmodes that describe the dynamics, but these eigenmodes are non-orthogonal, although all the modes are stable. And we'll get back to that in a bit. So from a detailed perspective, one could imagine deriving this equation from first principles, but it's a lot easier to basically go backwards and say it implies certain relationships in terms of the covariance statistics. So we can determine it in an inverse sense, both L and the statistics of the noise. Typically, these are done in EOF spaces, so they're actually very low order models. on the order of 10 to 100 degrees of freedom. And we can test to make sure that that linear approximation to the predictable dynamics is good. That's fairly straightforward. Then with an equation like this, the ensemble mean forecast is very simply derived. So we can determine forecasts for any lead time. Of course, these are probabilistic forecasts. It's really a Gaussian distribution due to the noise. So in fact, we can also issue categorical forecasts just from that ensemble mean PDF shift. So from a predictability standpoint, again, what we're interested in is essentially determining the difference between a predictable signal, this ensemble mean forecast signal, and an uncertainty due to noise. And this noise in a limb, we assume to be state independent. That makes it easier to calculate. In practice, from the theory perspective, this could have a linear state dependence on X that would give you non-Gaussian statistics. For short sample sizes, say 50 years, you might appear to think you had regimes, but in reality, you would just have skewness and kurtosis. We're going to ignore that here. It's very hard to determine that empirically, and it doesn't have a big impact in terms of the predictable signal that we're mainly focusing on here. So we are going to use the limb signal noise ratio. So there's a little bit of an error there because we're assuming that that noise is the same for any given state to identify the forecast with high expected skill. In the context of the limb, what that means is that we can use the initial state of the system and its predicted evolution to determine the forecast signal. So it's a state-dependent prediction of the forecast skill. But of course, again, this is a linear state-dependent prediction. And it will still be lead-dependent because obviously the effects of the noise are going to give rise to an increase in the spread with forecast lead time. So the way we've done this here, we're focusing in this talk just on the NAO. So I'm going to show NAO ensemble mean hindcast from the limb. And in the limb, we've trained it on 7-day running mean anomalies from the JRA 55 for the 79 to 2017 period. And we use a 10-fold cross-validation to get quasi-independent hindcast skill. So we're always trying to do a forecast using an operator computed on a different part of the record, the other 90%, and we just cycle through. This is the limb state vector. I won't go into the skill of this. Like I said, there's a previous paper where we looked at the comparison of the limb skill and the limb predictability estimates, both to itself, to the IFS and the CFS. And the IFS we use is this version, or dual version, which was operational in 2017, that we also got from the S2S dataset, and we've done a mean bias correction on it, although 20 years is pretty short to get a good bias correction, but that's what we have. So we'll compare that skill, and we'll also use the limb to identify the high skill forecasts and identify the dynamical processes responsible for that. And the measure we're just going to use for the NAO is just a simple correlation between the predicted and observed 7-day running mean NAO time series for this 20 years of winters. All right, so let's just start off with the skill. We're immediately stratifying the skill based on whether the limb is predicting ahead of time that it's in the top 15% of all forecasts or not. So, and then we look and see, well, how good was that prediction? Did we actually get a good difference? And the answer is yes, both for the IFS in black and the limb in this golden color. The skill of the NAO is considerably higher in the 15% of the times that we have pre-identified using the limb signal noise ratio that we would expect to have higher skill, and the 85% remaining, it is indeed lower. This is kind of a common thing with the limb. When the limb does badly, it tends to do very badly, which is related to the EOF truncation that we use. We don't have quite all the observed variance in the limb when we construct it. But these two are very close together, and you can see that the IFS and the limb are basically getting about the same skill from weeks 3 to week 6 in these high skill cases. All right, so what dynamical processes are responsible for this high NAO scale? And so to get at that, what we're going to do is we're going to dig into the dynamics of the system more by looking at the two groups of eigenmodes of the dynamical operator L, which very nicely fall into two subspaces. In one subspace, we have eigenvalues. We have eigenmodes which are associated with eigenmodes with a very long e-folding time, so they tend to be more persistent. They have very low frequencies, so they tend to evolve very slowly. They also tend to have fairly large anomalies in the SST and stratospheric components of the state vector. Or there's one which is actually purely stratospheric, which has no SST component, which is quite interesting. I'll show in a second. And then there's a larger subspace associated with what we call internal variability. And these are down here. These are all eigenmodes that tend to have very short e-folding times. They decay very rapidly. They're not very persistent. They don't have an SST component. Their stratospheric component is mixed, but they do have some. But basically, they're dominated by tropospheric variability. And the MJO is actually included in this internal space. And this is similar to results that we've had previously doing this sort of analysis, looking at the just tropical variability or looking at the PNA. There's a recent paper by Henderson et al. Where we've done similar approach. So now what we'll do is we'll take any anomaly, any state vector x, remember all the variables that we have in the limb, and we're going to express it as the sum in these two subspaces. So you can think of this as a dynamical filter. We'll look at one part in the internal space and the other part in this, what we call stratosphere SST space, and just write it in this sort of way. So just first, what does this space look like? I'm not going to go into this in a lot of detail. John actually has a teleconnections webinar next month where he's going to talk a lot more about this. He's looked a lot more at the implications of our limb on stratosphere, tropospheric coupling, and how things play out relative to Baldwin and Dunkerton kind of paint dripping. But just to give you a little bit of an illustration, if you do a composite on the NAM index, if you do a kind of an annular mean and look at the vertical structure with kind of a lead lag, you see that this one eigenmode that had no SST component actually looks very much like that kind of paint dripping picture. It really represents it quite well. And you get this descent of, in this case, height anomaly, kind of an average, on the NAM index. And that's associated with this kind of antic sea level pressure anomaly. I like to call it NAO-like, although maybe that's not entirely appropriate. And alternatively, if you do a composite composite on the NAM index at 300 millibars, essentially at the tropopause, one gets a somewhat different picture. You see some of this descent, but it's a lot weaker. And what mostly you see is a structure which has much more of a tropospheric and lower stratospheric characteristic, much more associated with the SLP anomaly that's much more annular, and a SST anomaly, which is essentially a non-canonical ENSO signature. And we've seen this in previous limbs in the past. And it tends to be associated with a tropical heating anomaly that does not project onto pure MJO, pure ENSO, or you could say it projects onto both. So basically, just a straight vanilla canonical ENSO won't give you this response. But this pattern is very important in terms of ENSO diversity, the different flavors of ENSO that we actually see. So it basically says that it's an ENSO dynamics that's driving, but not a simple Eastern Pacific El Nino. Anyway, John will go into this in a lot more detail next month. All right, so what we're going to do then is we're going to filter the data, like I said, and we're going to rerun all the limb hindcasts using only the stratosphere SST subspace portion of the initial conditions or the internal subspace portion. So just to show you what that looks like, this is a time series of the NAO in black. Same thing here in both panels. And then in green, I'm showing the two subspaces. So up here, the green is the internal subspace NAO, and here in blue is the stratosphere SST subspace NAO. Similarly, I'm showing the power spectra here. The black is the total NAO power spectra. The green is the internal subspace, and the blue is the stratosphere SST subspace. So there's a couple of things to note here. Number one, the internal subspace portion is already very highly correlated with the observed index, but this stratosphere SST subspace is not. So you might look at this and say, oh, okay, well, we've removed something that somehow makes it less NAO-like by taking out this stratosphere SST subspace, which in fact is the opposite of what I'm going to show you. And similarly, when you look at the power spectra, if you add the subspace variances together, you get 146% of the total variance. So that seems pretty non-intuitive. You say, well, they must have done something wrong. But in fact, that's exactly what you expect in a non-normal system. So again, these eigenmode subspaces are non-orthogonal. And what that means is that although the eigenmodes span the space of the system, when you look at the variance of each subspace, because they're non-orthogonal, you can add up individual subspaces to get an anomaly, but you cannot add up the square of each subspace to get the total square of the anomaly. In other words, the variance of each subspace added together is going to give you more than the total variance. And that's basically showing the importance of this issue of non-normality to the NAO amplification. In other words, internal subspace variability is sometimes covering up the more slowly evolving stratosphere SST subspace, and that covering up gives you initially small anomalies, and then as the internal subspace goes away, you're left with the stratosphere SST anomalies, and that becomes anomaly growth, and that becomes most of the skill. So in fact, the weeks 3 to 4 skill, in fact, weeks 3 to 6 skill of the NAO, both in the IFS and in the LIM, appears to reside almost entirely in this stratosphere SST subspace. So if you just initialize with the internal subspace, which seems so highly correlated to the NAO, seems to represent almost all the power, there's really no skill there. It's that non-orthogonal stratosphere SST subspace where all that skill is lying. All right, so finally then, the LIM, just to conclude, the LIM can predict at the time of forecast which NAO forecast will be skillful, and we find that this means that it can identify about 15% of both the LIM and the IFS weeks 3 and 4 NAO forecasts with high skill, basically anomaly correlations greater than 0.6 here. Again, the NAO anomalies and really all the states can be decomposed into 2 independent but non-orthogonal subspaces. An internal subspace, which although it dominates the NAO variability, it's largely unpredictable beyond about 2 weeks. And it's instead this smaller stratosphere SST subspace, which consists of this downward propagating stratospheric eigenmode, which looks very much like this paint dripping Baldwin and Dunkerton kind of picture from stratospheric sudden warmings, and a group of eigenmodes with joint stratosphere SST components in which it seems that the SST forcing is playing a much larger role, but a non-canonical ENSO forcing. So again, just to kind of summarize all of this, this means that high-skill subseasonal NAO forecasts are occurring in nature when initial stratosphere SST subspace anomalies are large but are covered up by internal subspace noise, and the LIM is able to identify these occurrences. To go into this in much more detail, I'm showing the 2 papers that have been published on this study. So thank you very much.
Thank you very much, Matt. Very interesting. So do we have any questions from the audience? Feel free to unmute yourself or post in the chat.
Hi, I had a question.
Go ahead.
The SST and stratosphere components, are those in some sense connected to each other, or they're just fortuitously coincident?
No, I mean, there's an evolution between the SST and the stratosphere and all the other components in the state vector. So every one of these eigenmodes is representing the evolution of this coherent dynamical eigenmode. For the most part, but not entirely, it looks like that the SST tends to lead. with the exception of this downward propagating eigenmode, which is clearly much more, it's independent of the SST and seems to be much associated with the more stratosphere troposphere coupled dynamics, the downward propagating signal that that people have been studying for quite a while.
Okay, thanks.
Thank you, Mike. Other questions? I have a quick question. So basically, at the time of initialization, would you be able to tell if basically your stratosphere SST subspace is going to be the one dominating the forecast at weeks 3 and 4?
Yeah.
So basically, you could say there's some kind of slow scale variability up there, or in the SSTs or in the stratosphere, and you'll be able to tell if that actually emerges and gives us skill in week 3 and week 4. Is that right?
Yeah, I mean, the idea is you're saying what part of the anomalies that you see at the initial time are representing essentially the slow subspace of the dynamics, and what part are representing the fast subspace. And so that gives you an idea of the predictable signal going forward. Obviously, in the context of the limb, you don't know the noise in the future. And that's another way of saying, you have some initial uncertainty. That's how it's basically showing up in the limb. But it also allows you to get some sense at the initial time of why you might expect to see an anomaly grow in a particular way. If you were to start, say, with a particular SST anomaly, which was being covered up a little bit by other variability, then that other variability, if it's fast, will tend to evolve away or decay away, and it'll leave you with this slower eigenmode, which is going to evolve. It might decay a little bit, but it won't decay as much as it'll make it appear that the anomaly has grown because of the removal of this fast destructive interference eigenmodes.
Very interesting. More questions?
Hi, yeah. So, nice talk, thanks. You showed that, I think initially, that the signal strength basically determines, or the signal to noise, sorry, determines the skill of the forecast. I was wondering what you saw, the value of this decomposition, because presumably the longer range signals are coming from the slower varying components anyway. So does this decomposition tell you anything about the predictability, or is it just used as a kind of attribution method as to why you have predictability?
Yeah, I mean, obviously in this case, in the limb, you don't technically need to know why. You could just say, well, here's my forecast signal to noise in 3 weeks, and so here's my predicted skill, and I'm just going to use that. And in fact, we have a limb where we're transitioning over to CPC to do North American, U.S. Surface temperatures year round. And that's kind of what we're doing there right now. We're just looking at what's the shift of probabilities, so you can always do that. But like I said at the beginning, I think it's important, for 2 reasons to do this. Number one, going to users, I don't think it's enough to just say, hey, we think we got higher skill this time. You have to give them some sort of story as to why. And so scientifically, we need to understand why this particular forecast is going to be more predictable than the one 3 weeks ago, which was, and obviously I tend to view sometimes the limb as the answer to the question, what do the dynamics of the real system look like? But it doesn't tell you how you got there, right? So this is sort of like a homework problem where I give you the answer and say, well, this is the subspace that matters. And now what you want to do is you want to try to figure out physically, why do these eigenmodes come up as the important predictable eigenmodes in the real physical system?
Thank you.
I have a question, Daniela.
Yes, go ahead.
Matt, it would be fair to say that for the period of time when the skill of limb is equivalent to the skill of the model has a good representation of the modes from which this skill it's coming? I mean, that's, or we still need to worry about model biases in represent mode?
Yeah, I mean, I would say, I mean, there's a couple parts to that. Number one, you know, is there absolutely zero predictable nonlinearity in the system, right? So you would expect that the model should do better than the limb, even if the system were entirely linear in this way, because I trained the limb on a finite period of time. So I expect the models to be a little better, even if it was purely linear. And then if there's any predictable nonlinearity, you might expect the models to be even better than that. So I'd say that gap, the fact that it's exactly comparable suggests that there's probably still some error in the model. And in fact, if you just look at week 3, right, and you look globally, there's a tendency for the IFS to be a little better than the limb. The limb is basically matching, you know, the IFS in a way which allows you to use it to diagnose, again, why the IFS has higher or lower skill, and when it has higher or lower skill. But it matches it, you know, like kind of step for step like that. So the IFS will always be a little better on average than the limb, and as the skill goes up and down, it tends to do that. But by the time you get to week 4, it's clear. And at week 5, in fact, the limb is actually better than the IFS, which again suggests that there's probably some errors now in the IFS, still at least in that 2017 version, which are inhibiting its skill some.
Okay, thanks.
Thank you, Christiana. Is there a last question from somebody?
Yeah, so if there's time, maybe I have a stupid question. So I'm only a student, and I would like to thank you for the instructive talk. But I wonder whether you can explain to me what it means if something is low frequent but rapidly decaying. So how are the internal modes the way they are?
Well, so they're eigenmodes of the linear dynamical operator. So if you have an eigenmode of a linear dynamical operator, they'll typically be, they're complex. You'll have a cosine phase and a sine phase. You could go back to, you know, kind of one of the earliest papers on low frequency variability, what we call S2S now. If you go to Simmons, Wallace, and Brandstatter, they go through this in terms of the eigenmodes of the linear barotropic model, for example. In fact, even back then, they were relating the eigenmodes, the leading eigenmode of that operator to kind of a flop between PNA and NAO. And the reason why you get that is because you have a cosine phase and then you have a sine phase. And the cosine phase is being modulated by something like cosine omega t, and the sine phase, which is imaginary, is being modulated by sine omega t. And then this is being multiplied by a complex exponential, so that you end up with an oscillatory behavior which has a decaying envelope. You know, you can think of it as a damped harmonic oscillator, if you like. The reason why they don't go to 0 is because you have noise in the system, right? So the noise is constantly kicking all the eigenmodes in a random way, and so you may have a particular eigenmode which is decaying for a while, but it gets kicked by noise and increases its amplitude again, or even changes sign.
Yeah, thanks.
Okay, thank you, Wolfgang. And with this, we would close the webinar. Thank you very much, Matt, for your nice presentation. And I would like to thank all the speakers again for their inspiring talks. I think we learned a lot about new methods and their applications to subseasonal predictability. From the side of the S2S committee, one thing that might be useful for you, or there's now a couple of S2S sessions at HEU that are advertised. One is on prediction processes and services, and the other one is on diagnostic tools and metrics. So some of you might be interested in these HEU sessions. I don't know if there's any other announcements from the S2S committee side. If anybody would like to, Frederick or Inge?
No, I don't think.
Very good.
That's all.
Very good. So then with this, I would like to thank everybody for attending, and you will receive emails about our next webinar as well. So thank you very much to all the speakers and all the guests and questions. Thanks.